Thank you, everybody, for coming to this Synopsys Simpleware joint webinar with Thornton Tomasetti, Johns Hopkins University, and Duke University. The title of our talk is Making It Real, In-Silico Workflow from 4D CT to FEA. So with me are my colleagues, Chris Goddard, John Jessiolu, Elham Raymar, myself, Karim Genç, and Christian Debus, and I'll allow them to introduce themselves. We'll start off with Chris.
Hi everybody, I'm Chris. I'm an applications engineer at Synopsys. So I have a PhD in computational physics, which focused on understanding chaotic and turbulent solutions that arise from numerical models for non-Newtonian fluids. I've had various roles in design engineering before joining Synopsys in 2018, where I assist with developing automatic image segmentation tools and processing tools for the Simpleware product.
Hi everybody, my name is John Jessiolu. I'm an assistant research scientist working in Johns Hopkins University. I have a PhD in electrical and computer engineering, and my research focus is image registration and segmentation, mostly on human brain and cardiac data.
Hi everyone, my name is Elham Raymar. I have PhD in mechanics, material, and structure. I recently joined to Thornton Tomasetti as a project engineer.
Hello everyone, this is Christian Debus from Thornton Tomasetti. I'm the VP of Life Sciences. I'm heading the Life Sciences team in Santa Clara office that you see in the background here. Part of the applied sciences practice. I have a PhD in mechanical engineering CFD many years ago. And after 7 years of working in business development at Siemens Digital Industry Software, I joined Thornton Tomasetti a year and a half ago to drive the adoption of In-Silico and digital twins in the medical devices industry. Thank you. Karim?
Yep. Hey, everybody. My name is Karim Genç. I'm the business development manager for the Simpleware group at Synopsys. My background is that I did an undergrad master's in biomechanics and a PhD in biomedical engineering. A lot of my focus was on bone fracture mechanics. So moving on to the presentation, just a bit of logistics here. Let me just move this along. So this is a presentation with the Q&A. The presentation is pre-recorded, but the Q&A will be live. The attendees will be muted throughout. You can submit your questions on the right here in the GoToWebinar questions box. We'll try to get through as many questions as possible. If we can't get to your questions, we'll follow up by email. This webinar is being recorded, so you'll get a link to the recording afterwards for you to download. So if there's any problems throughout the webinar, please report them in the Q&A toolbox and just let us know. So really quickly, I'll give a little overview of Synopsys Simpleware and who we are and what we do, and then we'll kind of get into the meat of our presentation today. So just to let you know a bit about Synopsys, we're a roughly $4 billion in revenue company based out of Mountain View, mostly focused in the semiconductor chips industry, from electron design and automation to manufacture and design. So with this, they acquired Simpleware back about 5 years ago, and a lot of that was due to our technology and our capabilities of handling very complex structures, organic shapes, which you get from human anatomy, and that has helped on the technology side of things within other Synopsys products. And as such, we've been able to grow within Synopsys quite nicely. So with regards to the Simpleware product group, which is who we are, we develop high-end 3D image processing software to go from 3D images to models. That's the 50,000-foot view of what we do and what we try to accomplish. And with that, we work with partners and collaborators on projects such as the one that we're about to show. So we have service and sales around the world, and we work with different customers in clinical life sciences applications, also on more of the industrial side of things as well, with materials and manufacturing. So what does the Simpleware product offer is basically an example here is an In-Silico trials type example. And that's really the focus of this presentation, is looking at In-Silico applications of simulation focused long-term in the regulatory space. So the idea is to supplement clinical trials with In-Silico virtual patients is the idea. And we're building up that workflow and building up that knowledge base through these collaborative efforts. So within Simpleware, we have techniques to process large numbers of data sets, create position optimized devices, and create in-silico models for analysis and simulation. And the idea is to speed up your in-silico trials to reduce cost. So to give an overview of this webinar, 4 groups, one from Duke University, ourselves at Synopsys, Johns Hopkins University, and Thornton Tomasetti, we teamed up to demonstrate a workflow for an in-silico study of an aortic frame deployment in 5 patients. So this is a proof of concept workflow, and we wanted to show multiple patients just to show that it can be deployed widely as a starting point. Obviously, it can scale up as well, but we thought this is a good starting point to demonstrate these capabilities. So just to give you a basic overview of the workflow, so this presentation will follow that workflow, going from the Duke data that was provided by Duke University, Paul Seegers and his group, provided the 4D CT data. So that's 4D CT scans of patients throughout the cardiac cycle. And then into Simpleware. So my colleague Chris will start things off by talking about the automatic segmentation and landmarking and that process that he did within the Simpleware product. And then over to John and the model morphing that he completed using his algorithms to morph the different time steps together. And then we'll pass it off to Elham to talk about the FEA of the aortic valve frame deployment and what she was able to do for this workflow. And we'll end with Christian giving us a nice kind of a summary overview of what was done and why, from his point of view on the simulation side of things and kind of the deployment of these types of workflows. So with that, I'll pass it off to my colleague Chris, and he can tell you about what was done in Simpleware.
Thanks, Karim. So we took 5 contrast-enhanced cardiac CT scans, which were kindly provided by Duke University. These were 4D images, so that's 3D volumetric data with 10 time frames over the cardiac cycle, capturing the full motion of the heart. We used Scanopi Medical to import each of these scans using our 4D processing tools. Here we are able to visualize the images, including real-time animations of the cycle and interactive live volumetric renderings. To extract the relevant geometry from the scans, I used our AS Cardio module, which is our machine learning tool for automatic segmentation. This tool labels the blood pool chambers and certain muscles, as well as identifying key points, landmarks on the anatomy. The typical processing time for this is about 3 minutes per frame, compared to having to do it manually, which can of course take hours. The output segmentation can be validated by the user before processing further, but in these 5 cases, no additional manual processing was required. The labeled data and point landmarks were exported from Simpleware for further processing by Johns Hopkins University. We'll hear more about this later. One of the key parts of this project was the ability to automate the entire process in order to illustrate a viable route for larger scale studies. All of the steps that I've shown so far have been implemented using our scripting API. So it's literally a case of pointing to a folder of DICOM studies and pressing go. The automation continues in the mesh processing stage. We need a prepared surface mesh for the first frame, which for consistency, we will then morph across all of the frames. For the simulations we'll be looking at later, it's necessary to isolate the aortic root and the left ventricle. I used the generated landmarks on the coronary cusps to define the valve plane, and our centerline tools to clip the aorta at a distance of 50 millimeters perpendicular to the centerline for consistent outlet boundary conditions. Using Simpleware mesh generation tools, I prepared the surfaces so that there are coincident nodes at the valve boundary between the 2 parts and an output mesh with a target edge length of 1 millimeter. Again, all of this was automated using our predefined set of rules and can be carried out for much larger study groups. I'll hand you over to John, who will describe the next steps.
Thanks, Chris. In my part of the presentation, first I'll briefly talk about the input data I received. Then I'll talk about the LDMM framework, which is a state-of-the-art registration tool. Then I'll talk about how I applied LDMM for the registration of cardiac data, and I'll conclude my part. So this is the data we received. We had 5 subjects. In this slide, you see the data for one subject only. So for this one subject, there are 10 time points of segmentation data for left ventricle and aorta. Also, for each of these 10 time points, we have points or landmark data shown in red colors. Our goal is to transform the surface data that is defined only on the time point 0 onto other time points. To be able to do that, we used the landmark data and the image data and calculated a consecutive registration between time points. So before going to details, first let me briefly talk about what is image registration. When we have biological images or shapes, any calculation of an image registration is simply a calculation of a transformation or a function between the spatial coordinates of these two images. For the analysis of biological shapes, we want our transformations to have spatial properties. The important property that we want is our function to be a diffeomorphism. A diffeomorphism is a function that's differentiable and also has a differentiable inverse. So what we gain by having a diffeomorphism? So when we do a transformation between images, any disjoint shapes still remain disjoint. We don't fuse multiple points onto a single point. Our connected shapes still remain connected after transformation, and we preserve the smoothness of object boundaries. Now, if we go to the tool that we developed in Johns Hopkins University over years, which is named Large Deformation Diffeomorphic Metric Mapping, which is abbreviated as LDMM. With an analogy from fluid mechanics, the registration process can be thought as follows. So let's assume that we have 2 images that we want to register, and points in the first image moves to points in the second image, like fluid molecules in this registration process. And the movement happens over time, and it has a velocity. Velocity is represented as a time derivative of this deformation, shown in equation 2. Here, the time parameter is an imaginary parameter that's used to describe the flow of these points between these 2 images. So the LDMM framework can be thought of as a minimization problem, shown in equation 3, where which has 2 terms, with the first term a regularization term, and the second term an image mismatch term or cost function. So the solution of this functional equation, or the minimization of equation, satisfies the following Euler-Lagrange equation. And if we want to summarize the LDM framework, we use a gradient descent algorithm to calculate iteratively the velocity field between these 2 images at each iteration, and then we integrate the velocity field to calculate our transformation field or deformation field. So to better understand the framework, let's focus on a simple example. In this example, on the left, we have a 2D circular shape. And on the right, we have another circular shape, but with a sinusoidal boundary. So we want to compute a transformation between these two images. When we apply the LDMM algorithm by minimizing this energy functional that I showed in previous slides, the third row shows the computed velocity field. So the velocity field is computed at each iteration. Then it is integrated to calculate the deformation field, which is shown in the last row. The deformation field is represented by deformation of the regular grid defined on the first image. And the second row shows the transformation of our input image I0 with the deformation for each time point, where this time point is our imaginary parameterized time parameter. And as you see, as the time goes from 0 to 9, our image I0 becomes more and more similar to our target image I1. So in the LDMM framework, I described the image registration algorithm. So in this image registration algorithm, the second term is an image mismatch parameter. But by replacing the second term with some other cost functions, we can apply the same registration onto different data sets. Like we can register point sets with LDMM landmark. There is a LDMM curve version. And there is an LDMM surface version for registering triangulated meshes. But for the data set I have, I use the input data is landmark points and image data sets. I use the landmark LDMM and image LDMM. So for the input data sets, there are 10 time steps. And I calculated deformation or a transformation between each consecutive time points, from time 0 to time 1, time 1 to time 2, up to time 9. So, for example, let's focus on time 3 and time 4. So, using the landmark data sets, first we calculated the deformation using the landmark version of the LDMM algorithm. Then also we use the image version of the LDMM algorithm. We calculate the second transformation. We compose these two transformations to calculate the final transformation between times 3 and time 4. So using all these computed transformations, we started from the surface data at time 0, and we transformed this surface data onto each of other time points. So here in this slide, you see the surface data is overlaid onto the image data with color cyan. To better show these surface overlaid onto image space, I removed the segmentation images. Now I only show the a 2D overlay of this surface data. I also show the triangulated mesh representation of this surface data in the first row. So this concludes my part of the presentation. I briefly described the LDMM registration tool. It is available for other researchers on our website. And thanks. Now, how I can pass.
Yeah, so in this part of presentation, I want to show you how we use the mesh data extracted from 4D CT to develop the computational tool. So for a specific patient, as it properly explained by John and Chris, we have 10 frame times for each patient, and we have mesh data for these 10 frames. So based on that frames, we measure the volume of the ventricular part, and then based on the variation of volume, as you can see here, we consider the corresponding aortic pressure in from the Wigger's diagram, and then we apply this pressure to the aortic part for the simulation of cardiac motion. For the rest of the anatomy geometry, we applied the alteration of displacement as boundary condition. So here I should say that one can estimate the specific patient aortic pressure based on the available ventricular and heart rate information. But in this study, we only use some general pressure from the figures, these figures, the diagram. Okay, so here you can see in left-hand side animation of cardiac and vascular motion that shows the contour of displacement with respect to the first geometry of the first frame for one patient. And then just to evaluate the accuracy of the applied boundary condition and pressure in the numerical model, we compare the geometry of CT data with the deformed shape from Abacus. You can see in right-hand side 4 frames that we have this conversion in simple wear. And as expected, because we use some general pressure diagram, we have a little bit deviation of the geometry around the aortic part, but we have perfect match for the rest of the anatomy. So based on this assumption, we went through the next step of the simulation. Aortic valve framed modeling. Here, we simulated aortic valve with 3 types of elements: beam element, shell, and solid. With the same deployment sequence, we deployed this frame, all these frames in anatomy. And then for the material property, we use the same superelastic plastic material for the frame. And we applied the same pulsation or same boundary condition and pressure to the anatomy just to evaluate the performance of each type of element to pick one of them for the rest of our workflow. So here you can see that we went through the details of numerical simulation for based on each element type. So if you look at that slide, you can see generally all of these type elements for the frame are functional. If we compare the result of these aortic valve with frame and without frame. But as expected, modeling the frame with beam elements is computationally more efficient model. And for the solid element, we saw that the solid element model is more robust with the better interaction performance for the simulation. That is why from now you can see just the result of solid element for the specific patient aortic valve deployment and the rest of the study. Okay, so we need to deploy the patient-specific valve. And again, in this simulation tool, we have the valve frame that was deployed in an ideal final position. And the real procedure for hard frame deployment and implementation has not been simulated here. And but we know that we can simulate the whole delivery system and set up the simulation to mimic the real deployment procedure for a specific patient. But in this study, we used 5 simple steps for the deployment of a specific valve for each patient. Okay, based on the pulsation simulation and then the deployment of the valve frame for each patient, we succeeded to simulate and use this sequence for 5 different patients. So based on this slide, you can see the whole procedure we have developed is applicable for multiple different anatomies, and also it can be appropriate to deploy the patient-specific device size, because here we use the patient-specific aortic root dimension, and we scale the frame, and then we deploy the specific patient frame and apply the specific patient pulsation and boundary condition and pressure. Everything is for a specific patient, and we simulated for 5 different patients. So from the simulation result model, we can extract different type of outputs, and then we can interpret these outputs by the requirements. For example, one of them can be the contact pressure variation through the cardiac cycle. So you can see here the response of the anatomy are totally different after the deployment during pulsation, and also the pressure distribution during the cycle for each specific patient also is not constant. So it shows that we can use such that information for device to study the device usability. We can see if the frame is fully placed to the vessel. We can also evaluate the potential for any retrogression flow or leak, or we can study if there is any frame migration or displacement over time for a specific patient, or we can compare patient to each other. So the other outputs that can be useful for evaluation of the device, specific patient device, is the stress distribution for the aortic valve. So we can, as you can see here, we have different response for the vessel from the vessel, and if one can see the differences between patient 1 with a little bit healthy looking anatomy and with the patient 2 that has a little bit abnormal type coronaries. And for each specific patient, for example, patient 2, 3, or 4, based on the irregular left coronary, right coronary, and aortic root geometry, we also can have focus on each patient and study the performance of the frame for different parts of the aortic geometry for patient, based on these stress distribution results. So not only we can evaluate the performance or the behavior of the vessel or anatomy after deployment of the frame, but we can also evaluate the mechanical response of the valve frame itself. Here you can see that we have the result of strain distribution of the frame for 5 patients at the same time frame. And from this result and the deformed shape of the valve frame, we can see that what is the effect of aortic geometry on the deployment of the valve frame deployed. Or one can use such that information to study the strain characteristic or do the fatigue analysis for the frame. So my colleague Christian will talk about the overall view of such that computational tool In-Silico trial.
Thank you, Elham. Actually, to wrap it up, I want to first thank everybody in the team for a great collaboration. It's a lot of players in the game. I specifically want to thank Becky also from Synopsys to manage the whole process, and everybody working in the background there from the data to making it a nice workflow. And I just want to briefly bring it back into the In-Silico context. What we're doing here is really to show how In-Silico is possible and has been done these days from an engineering perspective, so really automate that workflow. So at this point, we can sit back and have the whole thing run. We showed it for 5 patients, but of course you can extend that. At Tomassetti, we essentially have like this In-Silico toolbox that we work with, and with using tools like Simpleware and Abacus, as you were seeing. So there's this whole imaging to simulation workflow. Plus that can be extended, of course. You could parametrically describe anatomies and then extend the cohort size and things like that. We really went into the core of all this work is to show that process from image to simulation, show the modeling and simulation outputs. What we didn't go so deep into, but what we also need to be doing, of course, is the VV uncertainty quantification and verification validation. Down the road, if you want to look at bigger cohorts, of course, you will also probably apply reduced order models or even physics-informed AI machine learning tools, all things that we are developing and working with our clients at this point, and maybe even advanced visualization and VR for the communication at the end. To maybe the regulatory. So like on the right-hand side, you can see, so yes, we have the design and simulation validation portion. That's really what we talked about. But if you want to go full In-Silico, don't forget you also have to do your data management really properly. So then when you go to the regulatories and present your work, that it's trackable and really gets you to full success. The images in the middle to show you that the areas that we were talking about today, cardiovascular application, of course, they can all be extended with the whole tool chain that we saw today into orthopedics, or recently we're also working quite a bit with drug injection or drug delivery systems and things like that. Of course, that goes all the way into the pharma, but I think what we saw today, really applicable in silico trial application from beginning to the end, fully automated, was quite exciting. And I'm looking forward to do more of this work with this team. It was really, thank you again, everybody, for their contributions. It was fun and very productive. And with that, I think we'll give it back to Karim and do some Q&A. Thank you.
Yeah, thank you, Christian. And again, I'd like to reiterate acknowledging the folks here who came together to put a lot of effort into this work. My colleague Becky Bryant, definitely, we would like to acknowledge her efforts in coordinating a lot of this. Unfortunately, she wasn't able to be here in the webinar. And also Paul Seegers over at Duke University for providing the data, the 4D CT data for us. Without that, this would have not been possible. So we're grateful to all the collaborators here and everybody who came and our attendees. And let's get on to the questions.
So we're going to start entering into some Q&A. So I'll just request the panelists to unmute themselves so we can get started here. So one question for, I think this is for Elham and Christian, I think. In the workflow, is there any Abacus specific tools in the Simpleware software, or maybe even some plugins in Abacus for Simpleware?
Hi, yes, so the only thing that for the comparison of the geometry, I had the output from Abacus to Simpleware to compare the results, and then a specific tool in Abacus, I don't think. I mean, we try different things in terms of applying pressure or boundary condition, like different type of fluid application that we have in Abacus, but for here we try to simplify the simulation and we didn't use a specific parts of the Abacus or some. We use some, I mean, general tools in Abacus for simulations.
Maybe Chris, you want to comment on the interactions between Simpleware and Abacus?
Sure. So in Simpleware, our model configuration has a dedicated export for Abacus, so the INP file. And here you can set up the materials, contacts, node sets, shells as required. So that's the sort of the workflow steps that would typically be used for going from Simpleware into Abacus.
Great. Another question, is there a way to include tissue reactions such as fibrosis or incorporation of the stent in the vessel?
Well, I can say generally, yes, you can definitely make it more complex and higher fidelity model. Elham, you spoke about different types of models, beam, shell, and 3D that you were using, but maybe you want to elaborate on the other options there.
Yeah, for instance, yes, we can use as we said, different type of elements, and then for tissue, again, yes. So since the subject of this study was for the deployment and then the stent mechanical behavior or performance evaluation, we didn't consider a specific mesh or material model for tissue, but for sure we can add this part for the next study.
And we do currently work on such a project with somebody we cannot talk about, but it's definitely something that people are getting more interested in.
Mm-hmm. Let's see here. Let me see a question. This is probably a question for Chris. Organic geometries can be tricky to mesh without causing major distortion in your elements. What kind of problems did you have regarding your mesh, and how did you solve them? So I guess, Chris, since in this case we use the surface mesh, you can talk up to that, and then maybe Elham, you can speak to the volume meshing.
Yeah, sure. So for generating the surface mesh, that's done from the static frame for the first frame of the CT scan. So I didn't experience any issues at that stage. Our meshing algorithms are quite flexible for the inputs and can optimize the geometry. I guess in terms of the deformation, that's in the later parts of the workflow. So maybe Elham can speak towards that.
Okay, so for the I don't know if I understand the question correctly. If you're talking about the mesh for the stent, I don't know, or
so it's more about the organic geometries and any issues might have had. So more, I guess, the tissue versus the
okay.
stent.
So for that part, I go ahead. Okay, for that part, I didn't see any, I mean, issue. The mesh that I received from Simpleware was so, I mean, was quite, I mean, accurate in terms of simulation. I didn't see any specific problem to use that mesh for finite element simulation. And then, but we could use a different, you know, density for the mesh. So for the simulation, it's better to use, I think we have this tool in Simpleware to use a little bit coarse mesh and to make the simulation more faster than fine mesh. But I don't know if I answered the question, but I
think that should be helpful. Let me go back to another question. Is given pressure and motion, did you estimate properties for a muscle model in the heart? If so, how do they compare to the literature values?
Yes, for the pressure, I try to use, as I said, I use some general information from the literature, but in terms of the response and then, you know, the motion, I had the information from different frames. So I try to mimic the pulsation and then apply boundary condition to mimic the same pulsation based on the frame information or mesh information for the ventricular part. And then for the applying pressure, as I said, we could use the other tool to, for example, to extract a specific patient pressure. But here I use some general information from literature for the pressure, aortic pressure part.
Okay. Here's an interesting question here where it says, as aortic root deformation is predicted, not prescribed, have you compared it to image to check the accuracy of deformation prediction at the aortic root? So my understanding, I could be wrong, was that it's actually prescribed motion because we segmented each time step of the cardiac cycle and then morphed them all together. Is that correct? Maybe Chris and Elham, you might be able to answer that.
Yeah.
So it's okay. So it was prescribed. I guess the question is, have you compared it to image to check the accuracy of the deformation prediction at the aortic root? So I guess
yes, I did. In the second slide of my presentation, I showed that the accuracy of the applied pressure or, you know, boundary condition to compare in Simpleware. I compared them, and so the STL file from Abacus or the deformed shape of Abacus with the frame that we had in Simpleware, and then we compare those to just to see if the assumption are correct or not. And you can see that we have, I mean, since we use some general pressure, we have a little bit deviation for aortic part, but for the rest of geometry, we have perfect match.
Okay. Great. And maybe Chris, and maybe you can speak to the segmentation process. I mean, it was fully automated, correct?
Yeah, that's right. So it was AI segmentation, fully automatic. Our tools are a one-click solution to generate the segmentations that you saw.
Okay. Okay, one last question here. When you talk about automatic segmentation of the aorta, does that refer to the aortic lumen or wall? So I guess that's for you, Chris.
Sure, that's just the lumen itself in this case.
Yeah, and I should mention that AS Cardio is our off-the-shelf tool, and we do develop fully customized AI tools for customers in a framework called Custom Modeler. So this is where we can take AS Cardio and augment it with your data, or we can start from scratch with your data, and it'll do the automated segmentation and landmarking and measurements and things like that. So if that's of interest, obviously get in touch with us. We'd be happy to chat. I think that's it. We're going to call it for time here. I tried to get through as many questions as we could. If I missed you, we'll try and we'll answer over email, and also just everybody here will get access to the recording. So with that, I would like to thank all the panelists, everybody who put a ton of work into this, my colleague Rebecca Bryan, who is organizing a lot of this, and Paul Seegers over at Duke for providing the data sets for this. Without that, this project wouldn't have been possible, providing some nice 4D cardiac CT data. So we're very appreciative of that. And then John over at Johns Hopkins for helping us with the morphing, and Elham to run these pretty hefty simulations, and Christian for overseeing a lot of that over at Thornton Tomasetti. So with that, I'd like to thank everybody, and until next time, take care.